Hi everyone, I'm Prahalit, and I'll be presenting Lab 5, which explores the motion of a falling slinky. And so, in essence, this was kind of a choose your own adventure style lab, and we had a lot of flexibility in how we could approach the modeling and analysis of our system. So in this experiment, we analyzed a video of a slinky falling through the air using two main tools, which are the tracker for video analysis and glow script for simulation. And so the ideal goal was to predict and interpret the slinky's falling behavior by building a computational model. And so while we were able to simulate the motion using physics principles, the model's predictions didn't fully match the tracker data in the end, which gave us some interesting takeaways about the limitations of our approach. And so, for the foundational concepts, we grounded our investigation in several key physics concepts. We used kinematics and Newton's second law to predict motion. We used drag forces to account for air resistance, and obviously had equilibrium specifically to how it related to the slinky's initial state. And we also used a variety of modeling tools, from visual scatter plots and position velocity graphs to time-based analysis and a glow script simulation. And so, all of these combined to give us a multi-perspective view of the slinky's dynamics. And so the math behind the lab was centered on three key equations. So there's gravitational force acting downward on the slinky, as you can see there. There's also drag force, which resists the motion and is proportional to velocity squared, and Newton's second law, which we use to update the slinky's velocity and position over each time step. And so these equations drove the numerical model we built in GlowScript. So when setting up the simulation, we place the slinky sedentary mass at the origin, and we use a meter stick held by the person in the video as a reference for scaling. And we had to assume that the height was about 1.75 meters. And we also had the slinky's mass measured in at 0.218 kilograms, and we began the simulation assuming it was initially at rest. And so as for our experiment steps, we first or here. As for our experiment steps, we first loaded the video into Tracker, and we use it to monitor the movement of the slinky center of mass. And then something interesting that we noticed along the way was that the slinky's center of mass stayed nearly still until the top collapsed down to it, and after that, the entire slinky began falling together. We then exported this data into GlowScript, where we simulated the forces involved, including drag and internal tension. And to further explore the data, we also built a model in Excel for plotting and comparison. And as for the code, the slide shows a portion of the GlowScript code we just used. We calculate the net force in Slinky, and we update its velocity and position over time. We integrated all relevant forces and visualized the Slinky's fall frame by frame, which gives us a more complete sense of how it behaves dynamically. And the results are shown here in two colors. So the orange line represents the real world data tracked using Tracker, and the green line shows the simulated data generated by GlowScript. And so while the two sets of results started out fairly close, they began to diverge as the motion progressed, which indicated that some of the forces or factors may not have fully been captured in our simulation. So yeah, as for some assumptions or sources of error, we had to, I guess, keep in mind a few key assumptions that are for potential errors. So Slinky's motion was recorded in a high-speed sequence, which resulted in only a handful of frames capturing its movement. And so therefore, the tracker experienced difficulties accurately tracking each step of the Slinky's trajectory. So we had to assume that the Slinky's center of mass began at the origin and that no drag acted until the Slinky began falling. We also had to estimate the reference height based on the holder's size. And one of the big challenges we had was that the high speed video only captured a few frames of the fall, so the tracker couldn't follow the motion very smoothly, since we don't have like an 8K video. And of course, bugs in the code or tracking issues could have contributed to some of the discrepancies, as you can see. So, like coding glitches in essence. And so, despite those issues, the lab had a lot of good positive outcomes as the computational model provided an accurate simulation of the Slinky's motion, and using the tracker offered a workable data set for analysis. We also realized that were able to show that the GlowScript code operated reliably with no reported errors. And so, for us, the main challenge was reconciling the differences between the tracker data and the simulation, as a high frame rate compressed the fall into just a few data points, which made matching the motion over time more difficult. And so, in conclusion, this lab gave us a deeper understanding of how to simulate real world motion using physics and programming. And while our simulation didn't perfectly align with the experimental results, it still captured the general behavior of a falling slinky. And we were able to work with a lot of fun concepts like drag, equilibrium, and Newton's second law, and it was a valuable learning experience overall. Thank you.